Hello everyone and welcome to the demonstration of our efficient and compact offline chip-scale power supply, which is not only suitable for AC input voltages but also supports a wide DC input voltage range. Power supplies are among the most important components of all electronic devices. In many applications we can find tens or even hundreds of them. In a mobile phone, for example, they are required to deliver energy to the sensors, to the display and to the camera, for example. A growing field for power converters are low-power decentralized applications, as they are required, for example, for the remote control of a light bulb, for the temperature and the humidity sensors required to control a heater, for the airbag sensors in e-cars, or for the position sensors in industrial applications. So now let's take a look on the available power supplies for the target applications. We could use energy harvesting to supply our applications, but due to its low power density, it's limited to about 1 milliwatt, which is not enough for many of the target applications. At higher output powers, we could use discrete power modules, which are already available at the market. They show a high efficiency at high output powers, but many of the target applications only need a few milliwatts, and in this low power range, the discrete power modules show very poor efficiency. In addition, they are often way too large for many of the target applications. So we have a resulting power supply gap between the energy harvesting and the discrete power modules, which needs to be closed. And in this demo, I will show you an efficient and compact power supply which closes this gap. And this is how this tiny converter looks like in real. You can see that it is significantly smaller compared to a conventional converter. I guess everyone is eager to see it in action, so let's plug it into the AC mains. After plugging in, the AC-DC converter starts to convert the AC input voltage down to a 3.3 volt output voltage. This voltage supplies a display, an IR receiver and a microcontroller. The IR interface can, for example, be used to set the background color of the display to green, to red, or back to the automatic color change mode between green and red. The converter consists of the chip itself, a power inductor, an output capacitor and an optional external buffer capacitor, which is only required for high output powers up to 300 milliwatts. For an output power below 50 milliwatts, we can use the on-chip buffer capacitor. The power converter is suitable for all common grid voltages and a wide DC input voltage range of 15 volt to 325 volt. The output voltage can be set between 3.3 volt and 10 volt to supply a wide range of applications. The maximum output power is 300 milliwatts, which perfectly closes the existing power supply gap, and with 73.7%, the peak efficiency of the converter is higher than most state-of-the-art power supplies. On chip we have implemented a rectifier, an active zero crossing buffer and a DC-DC converter. The active zero crossing buffer allows to reduce the required buffer capacitor by more than 400 times compared to the conventional passive buffer approach. The active zero crossing buffer is turned on right in the moment the rectified and buffered input voltage drops down or below the minimum input voltage of the DC-DC converter. And this is marked with an A in the diagram. The DC-DC converter uses two modes of operation, a resonant mode for input voltages above 150 volt and an interval-based constant on-time mode for voltages below 150 volt. And both modes of operation enable a high converter efficiency and a high DC input voltage range at the same time. Finally, let's take a look on the transient measurements. For this purpose I have prepared a second demo board, which is already connected to the grid and to the oscilloscope. The measurements show the 230 volt grid voltage in black, the rectified and buffered converter voltage in blue, the voltage at the inductor node in red and the 3.3 volt output voltage in green. We can see that the active zero crossing buffer turns on just as the input voltage drops below the minimum input voltage of the DC-DC converter, which is indicated by the spike in the rectified and buffered input voltage. We can also see the mode change between the resonant mode and the constant on-time mode at 150 volt. And we can see that the integrated closed loop control does a great job at keeping the output voltage constant at all time. Now we are at the end of this demonstration. I hope you enjoyed it. You can find a detailed description of the converter in our paper, and thank you for watching this demo.